Okay, welcome back. So we're going to be starting the MET lessons. There is one POF lesson still to do, but we're going to be starting the MET today. And we're going to be starting with stability, quite important subject to do because it actually underlays the sort of foundations for a lot of the other MET subjects you're going to do, notably things like thunderstorms and fronts. So if you can understand stability and the nuances behind temperature, movement and moisture, then it'll help you understand the next few MET lessons a little bit better. This is the way I like to do it, and I like to break down stability into two major parts, so temperature and movement. So we'll start off with that one. And you don't need to do a scratch pad or anything like that. I'm just going to do one now though, just to give you a little bit of depth understanding. So the first part of temperature makes a bit more sense to you, but again, you don't really need to do this in a brief or a lesson. Okay, so let's have a look at a parcel of air. So here's the Earth's surface. Here's the sky, if you like. And here is our parcel of air. Down here, it's all surrounded by normal air. And then in here, we have maybe a slightly different composition of air. Maybe it's warmer air, maybe it's just slightly more moist air. Doesn't really matter. Okay, so if I take this parcel of air and I move it upwards, there's going to be a number of things that happen. And why that happens, this is what we're looking at describing in this little scratch pad thing to start with. So around this parcel and all the way up to the troposphere and to a certain extent above, there's a lot of air. Air has weight, okay, it's around about 1 kilogram per square meter. And that's why we feel air pressure. So the further up in the atmosphere we go, the less air we have above us, less weight we have above us, and therefore the less pressure we have. So you can imagine this parcel of air sitting in a column. And above this parcel of air here is lots and lots and lots of square meters of air, which all weigh a certain amount of kilos when you add it all up. So therefore, right at the bottom here, we've got a great big column of air pushing down on that parcel. Now, if we send that parcel up in that column, so up in the atmosphere, whether it's moved through convection, it's pushed up through orographic lift, it doesn't really matter. If we move it up, then essentially when it gets to this level here, there's going to be less air above it, or less weight of air above it. And if there's less weight of air above it, then there's less force per square inches acting on that parcel of air, therefore there's going to be less pressure acting on that parcel. And if we think of a parcel like a balloon, then that parcel is now able to expand because the pressure's reduced, so it can expand and the volume can get bigger, and that's exactly what it does. So our parcel has now expanded. The thing to remember before we go into that though, is that inside this parcel of air is air molecules of various different elements, and they're buzzing around really, really quickly because they are a gas. And so they're moving around very, very, very quickly and bouncing off each other. And ultimately, the closer they are together, the more chaotic it is and the more sort of kinetic energy is being produced by the bouncing off the walls, bouncing off each other. As we move upwards here, we can see that the space is increased, and also as that space increases, the walls of this parcel effectively move away from those particles as they try to rebound off the walls. So all of that comes together to reduce the speed of the actual particles within the air. And we give ourselves more space for them to roam around, and at the same time, we slow those particles down. So the important element to add in here is that within most of the atmosphere around the world, we also have water molecules inside a parcel of air. There's generally water vapor in most air you find around the world, unless it's absolutely dry. So what happens to these? Well, these guys are moving around at a high rate of knots as well, creating their own chaos. And as the volume of this parcel grows, the water molecules can act in the same way in that they can slow down. Okay, so now we've got our molecules buzzing around, and we understand that the space increases as we go up. The next part to understand is that temperature is proportional to kinetic energy when we come to gases. So bear in mind that kinetic energy is proportional to the velocity of the particle as well. We can see that as the velocity of the particles slows down due to the enlargement of the volume, the kinetic energy is also going to reduce. And if the kinetic energy reduces, the temperature is going to reduce. Now, if we've got water vapor or water molecules that are buzzing around at a high rate of knots, they're going to be a vapor because they're moving at that sort of speed and they've got that amount of energy. If we now remove the energy, the speed from those water molecules, then they turn into liquid. And so essentially, if we can cool down this parcel to its dew point, then we can actually force the condensing of some of the water molecules within it. And what does that look like? Well, we can see that outside the window quite often because we see little clouds. And that's exactly what's happened. And so all inside that air parcel, you're going to get condensation and a cloud forming. And this is the difficult bit to understand. So if we are removing energy from these water molecules because they're buzzing around really, really fast, and we're taking energy away from them to slow them down, that energy has to go somewhere because now what we have is just slow water molecules that form clouds. So if we've taken that energy away, where's it gone? How have we taken it away? Well, it's been taken away in the form of latent heat. And so we're actually releasing heat into this air parcel by turning those water molecules into liquid. So if the heat is being released into the parcel then heats up. So what we find is at first it cools down a little bit as it rises and expands, but then when we release that latent heat, it actually warms up a tiny little bit, and then the temperature reduction in that parcel isn't going to be as great. Remember that when we come to thunderstorms, and also remember that as we now move into the beginning of the actual stability lesson, and hopefully that will make a bit more sense. So, like I said, we're going to start with temperature, and we're going to talk about lapse rates. So here we are again on Earth, and we've got two parcels of air which are sitting in amongst the rest of the normal atmospheric or environmental air around our airfield. Let's say this is our airfield here. There you go. There's a runway or two. Okay, so this air particle here, or this parcel here, has just got air molecules in it of various kinds, oxygen, whatever elements you want to decide is in air. There's no moisture in there whatsoever, it's completely dry. So thinking about what we just talked about, so if I take this dry parcel of air and I send it up into the atmosphere, then generally speaking what we find is that it expands and it cools at a relatively datum rate of dry adiabatic lapse rate, which is about 3 degrees. And that's 3 degrees per 1,000 feet. So when we get up to 1,000 feet, this parcel of air would have cooled by 3 degrees from its original figure. So if we started at 15 degrees down here, and for whatever reason this parcel of air was sent up in the atmosphere, when it got to 1,000 feet, it would be down to 12 degrees, and that's dry air. Now we'll look at saturated air. Now, word of warning here, saturated air essentially is a cloud. So you're going to see, if it's saturated, you're probably going to see actual water moisture in liquid form. But we're talking here about the saturated adiabatic lapse rate. And like we just talked about, because we're going to get that release of latent heat as the parcel expands in the atmosphere as it rises, and so we're going to get the cooling first of all, followed by an additional marginal amount of heating from that latent heat release. We're not going to have quite as much of a lapse rate, and that's why we see a lapse rate down towards about 1.5 on average. Which means that when we get to the 1,000 foot mark, if we started at 15 degrees down at the bottom here, then when we get up to the top there, we're going to be about 13.5 degrees. Point to note, or a bit of depth knowledge to take away, just remember, once we've got up to that 1,000 foot, there is less moisture in that parcel. That's something just to take away for a little bit later on. So that defines the two extremes in terms of moisture content. So completely saturated parcel of air where it can't hold any more moisture. Therefore, as soon as you get to that dew point, it's going to release moisture in the form of liquid, and then you're dry. The other lapse rate we can have, which is the lapse rate that you'll find above any airfield on any day or any point on the planet on any day, is called the environmental lapse rate. So the environmental lapse rate is calculated by the Met Office every day. They go out with a balloon, they release it in the atmosphere, it goes up to the troposphere, wherever it goes, and it takes temperature readings at every 1,000 foot or so. And that gives them a bit of a graph that they can build, and they can work out the environmental lapse rate for each portion of the atmosphere. So you're not going to get this sort of linear 3 degrees, but for the purposes of today, we're going to pretend it is. So that's the environmental lapse rate, the temperature change in the atmosphere above your airfield on any given day. So the next thing before we go on is we're just going to define the International Standard Atmosphere. It's not essential, but it gives you a good starting point for when you do this lesson. So the International Standard Atmosphere, which seems to be based pretty much on England, is temperature of 15 degrees at mean sea level, with a lapse rate of about 1.5. Sorry, not 1.5, 1.98. And then you also got your pressure, which is completely irrelevant really for this particular lesson, 2.5 millibars. But they're the international standards, and that's what we're going to base our little graphs on in a second. So that's temperature, and that hopefully gives you an understanding of why the temperature changes as we go up, and that's why we get that lapse rate. So the next thing we're actually going to talk about finally is stability. And this is what you've probably seen done to start with. So stability can be broken down into 3 different statuses. And we can think of this as an aeroplane or a building, which when you move it, essentially you're looking at its resistance to that motion from its point of equilibrium. So starting with the first one. So we've got a cup, a U-shaped cup with a ball in the middle, and the only thing holding that ball at the bottom of that cup is gravity. Now, if we take a force and we apply a force to the side of that ball, the ball is going to move up the side of the cup. And it doesn't really matter how far. If we apply a small force, it can go up a little bit. A large force, it's going to go all the way up to the top of the cup here. But the bottom line is gravity is always going to bring it back down here. It might go back up this side and oscillate, but it'll always end up back at the bottom again. So no matter how much force we apply to that ball, it'll always end up back down the bottom or back at its point of equilibrium. And we call that absolute stability. So the next one, as you can probably guess, it's the other way around. Here's our ball. Again, same force is acting. It's only really gravity that's acting on this ball at the moment, and it's holding it nicely at the top of that cup. However, if I apply a force to the left or the right, it's going to move it off that point of equilibrium there. Gravity is going to pull it down this side of the cup, and there's no force resisting it, or importantly, in comparison to this one, there's no force preventing it from moving away from its equilibrium. So there's no prevention, and therefore we have absolute instability. So the last one, our little middle ground, here's our flat piece of ground, flat-ish. So in this case, we've got gravity pulling it down against the ground, but if we want to look at the semantics here, we've got friction of the ground, which is going to slow it down. This is the only other force acting on it. So if I apply a force, again from the left here, if I apply a large force, it's going to move a little way. If I apply, a long way. If I apply a little force, it's going to move a little way. The bottom line here is there's nothing preventing it from moving. However, there is something restricting it from moving. So it can move, but how far it moves is dependent on how much force we apply and also how much friction is resisting that movement. So it's a restriction of movement. And that we call two different things. We can either call it conditionally stable or conditional stability. So there are three statuses. So now we can apply our three statuses to everyday life. So here we are with temp, altitude. So let's be at our airfield again, over here. And the Met Office has sent that balloon up for the day. And for whatever reason, they've come back and they've found that the lapse rate above our airfield is around about 1 degree. So it's a 1 degree difference above a 1 degree lapse rate above our airfield for the rest of the day. So we can call that lapse of 1 degree. So that means if we went for a datum temperature down at the airfield, so we look at the thermometer before we fly and it's 15 degrees, we know the lapse rate today is 1 degree, we know that when we get to 1,000 feet, it's going to be 14 degrees. Okay, so we're standing on our airfield and then for whatever reason, some air mass comes over from a nearby city where it's been completely dried out, there's no moisture in the air whatsoever, and it moves over the airfield, and as it moves over the airfield, it gets pushed up by a hangar or some convection on the airfield for whatever reason, and it starts moving upwards. Just like here, as it moves upwards, it's going to expand, it's going to cool, but it's going to cool at about 3 degrees per 1,000 feet. That's what we find. Is that as it gets to 1,000 feet, it's actually going to be 12 degrees. Likewise, a little bit later on in the day, a big air mass comes over from somewhere else in the country, maybe the coast. It's full of moisture and it's saturated and it gets pushed up again as it moves over our airfield. But that's going to cool at 1.5 degrees. So when it gets to 1,000 foot over our airfield, we find that it's actually gone down all the way to 13.5. So we've got a parcel of air over the top of the airfield, which is all wet, and another one which is all dry. The difference is at 1,000 foot above our airfield, it's 14 degrees Celsius. So these two parcels of air have found themselves surrounded by what is essentially warmer air. If it's warmer air all around them, then what they find is that they are going to be more dense and therefore much less buoyant. And so this parcel here and this parcel here is going to be sent packing back downwards again. The movement that these parcels are going to experience due to the momentum as they reach that 1,000 foot point is going to be limited and they're going to be pulled back down again. And therefore, any weather effects that could be seen from them is going to be stopped and we're going to get what is known as absolute stability. And again, you can look outside the window at this point if you've got windows and wherever you're briefing this, and you might have a extremely stable day. And the sort of stuff you'll see is, maybe relatively boring weather. It might be just stratus clouds out there. If you can get a Met report and find out what the actual stability is for the day, you could look out the window and just say, oh look, it's a stable day today, and you can see that because you've got stratus clouds or very little movement above the cloud tops there. They're very low cloud tops. Okay, so the next one. And you can rattle through these now because you've already obviously set the scene. So on this airfield, for whatever reason today, the balloon goes up and it finds that actually the temperature is reducing rapidly as you go up through the atmosphere. And it's finding that the lapse rate is 4 degrees for the day. And again, that lapse rate has been caused by all sorts of different elements on the airfield. So convection, condensation, radiation can make that temperature reduce much faster. So today it's 4 degrees. degrees. You can use it any temperature you like. Whatever the standard temperature is at your airfield usually helps to explain the situation better. Here's our 1,000-foot mite, just as a bit of a handrail. So, same airfield, different day, 4 degree lapse rate. Parcel of air comes over from a town or something like that that's really dry. It's got a 3 degree lapse rate, and we end up with exactly the same gradients. But the difference being that the temperature above the actual airfield due to the environmental lapse rate is down at, 11 degrees. The dry parcel has reached the top, that 1,000-foot point, and it's reduced down to 12 degrees. And as always, we're down at 13.5 for the moist one, or the saturated one, which means that at this level here, we find that the air around these two parcels, whether they're dry or saturated, is actually a lot cooler. And these two parcels are both warmer. And what that means is they're going to be less dense and more buoyant than all the environmental air around them. And so they're going to go piling up in the atmosphere. And you can see there's quite a considerable difference. So if it's a moist parcel of air, that's quite a considerable difference in temperature. So it's probably going to have quite a lot of momentum, quite a lot of force driving it upwards. And this is absolute instability. And again, if you've got a window, look outside. If you can see lots of cumulus with really, really high tops, it's a good unstable day. So the last one then. So the environmental temperature, the environmental lapse rate for the day, let's say it is our ISA for once. We've actually managed to get the same old lapse rate that is the international standard atmosphere. And it's decreasing by about 2 degrees. There we go. Which means our saturated one is doing its normal thing at 1.5. And our dry parcel of air is cooling at 3 degrees. We'll start at 15 degrees. And just in case this has caused any confusion at all, this is the international standard atmosphere. So this is the sort of the general average around the world. But just because it's 15 degrees Celsius at mean sea level doesn't mean your lapse rate is always going to be 1.98. Like I said, these are just the sort of base figures that you can sort of datum yourself on. The environmental lapse rate for the day, you might have 15 degrees at the airfield centre, but the environmental lapse rate, like I said, is dependent on wind conditions, condensation, moisture content, all that sort of stuff in the actual atmosphere of the day. So here we go, back to the conditional stability then. So we've got our lapse rate at 1.98, we've got our saturated parcel, which reaches 1,000 feet and finds itself at 13.5 degrees again. And our dry parcel coming over from the city that's just suddenly arrived as a bit of a visitor at the airfield. And that's arrived, as always, at 12 degrees at 1,000 feet. So we can see, in comparison to the air around it, This parcel here is warmer, more buoyant, and it's going to go up. But if we've got dry air over the airfield, it's actually going to come down, or at least stop going up. So we can see here, dependent on the level of moisture in the air parcel that decides to visit our airfield that day, we could have stability or instability in that visiting air mass. And again, looking out the window, this is a relatively common situation, especially in the UK. And if you look out the window, you'll see all sorts of different cloud types, and you may well even just see quite thick rain clouds, because if you've had a moist air mass come over, then that's going to get pummeled upwards. And if you've got a dry air mass coming over, you might see a bit of blue sky and a bit of a gap in the sky. So they are the three statuses of stability, and they are the three graphs that hopefully will make a bit more sense to you now. And you can see it's been broken down into temperature and why the temperature changes, and then add into that why with a temperature change you get differences in movement. That's all you need to do for the brief. All I'm going to do here is just add on a little bit of a sort of top tip for you to understand. So the Met Office actually does use graphs a bit like this. They're not obviously as simplistic and linear as this. And here's one here now. And they are called a TEFI graph. And it's actually what they spend most of their time sort of analysing and predicting the weather on. Because what they do is they'll have, as you can see in the middle there, the line, the sort of wiggly line going up, that's the line that's been produced by that Met balloon, giving you your environmental lapse rate. And realistically, the air isn't saturated on the surface most of the time, because otherwise it would be probably in fog half the time, wouldn't we? So you can see the air is drying, or cooling, sorry, at the dry adiabatic lapse rate here. There's a little straight line, which is a 3-degree gradient up to a certain level. At that level, it's hitting its dew point, and then it becomes saturated, and then we get a saturated adiabatic lapse rate from that point onwards. And I spoke earlier about how, as the moisture content starts to reduce, because we're creating clouds and removing moisture from the air, that's going to affect the lapse rate as well, or the amount of latent heat produced. And you can see there the actual saturated lapse rate is sort of bending over slightly as well. So that's the sort of product that actually gets produced, and that's why these graphs are taught to you and why they're kind of important really to understand from a foundation point of view. Anyway, don't need to talk about that. You can mention it as depth knowledge, the TEFI graph, and that pretty much concludes the lesson for today. Hope that's been useful. As always, any tips, errors that I've made, or questions you have, please put it in the comments below. If not, continue to subscribe and give me a thumbs up if you like it. Thank you very much.